Today is our 6th class. My, how time flies when you're having fun. You have your take-home quiz today, which is due on Wednesday. So I want to just read the instructions to you right now so that if you have any questions, or in case you don't fully read the instructions, that at least they've been read to you. You can use whatever resources you want for this quiz, except for the help of another person. So someone's asked me later, can I use a computer? And I said, sure, as long as you attach whatever information you get in a printout from a computer on here, it's fine. You may not seek assistance on this quiz from a Math Studio faculty, so I won't see you in the Math Studio anytime on Wednesday getting help from an instructor, or a peer tutor, or a classmate, or anybody else, any friend who may have had the class before, a friend who's, a math major or whatever. Put your final answers in the blank lines. So I expect to see just the final answers here. And then this is a critical part. Show all your work. Note, in bold, if you do not show how you arrived at your answer, then you may not receive credit for the problem, even if the answer is correct. You will not receive credit. It's not a may, it definitely will not. So I need to see how you arrived at each of these answers. You have to show the work either here or on a separate worksheet. And please, on your worksheet, sometimes I get worksheet with work, like all in different directions, and there's no labels. Like, so if you're working on, for example, number 1, please put number 1 and show me your work, okay? So are there any questions on what's expected for the take-home quiz? What if you know you're not going to be here Wednesday? What are your options? Take a picture, scan it, get it to me somehow, drop it off Tuesday, anytime Tuesday, put it under my office door, or hand it, no, you can't hand it to a classmate. That's not going to work. But if you have another friend that is coming on Wednesday and they can get it to me by 10:40, that's fine. Okay. All right. So that I'll distribute that at the end of class. So I want you to notice that Friday and today we've been covering 2 sections, but we're really focusing in on section 5.1 today, which is a system of linear equations. And what we were doing on Friday was we were doing those story opportunities using 1 variable. And today we're going to be allowed to use 2 variables, which is easier for some people. And if you use 2 variables, then you need to have 2 equations in order to find the common solution, which is where we started today's preview activities, with the idea of having 2 equations with 2 unknowns. This is called a linear system. And when you find a solution, a common solution for this, it's an ordered pair. If there is a common solution, it's an ordered pair, okay? So you actually have 2 choices. You either have lines, let's say in this particular case, our lines intersect down here at that common solution for -1. But you have 2 other choices for a system. You could have, and not recognize from the equations, parallel lines, which has no solutions. Or sometimes you actually get the exact equation, and again, because of the algebra, you may not recognize it. So if you get the exact equation, then your solution is an infinite solution set, because every single point that's a solution for one line is exactly the same solution for the other. So when you see a system of linear equations with 2 unknowns, 2 equations with 2 unknowns, you could have 1 solution in common, 1 ordered pair, no solutions at all, it's an empty set, or an infinite number of solutions. So we're going to be focusing in this class on a common solution like 4, -1. Okay? So visually, you find that common solution by looking at the graph and finding the point of intersection. So the point of intersection is the common solution. Okay. to the system, to both equations. If you put 4 and -1 into each equation, the left side equals the right side, which was number 1 in the preview exercises. We had you find that. Now, what a lot of students sort of do when they're asked to graph linear equations like this is they will automatically take this equation and solve for y, which could have several different opportunities for errors because you're so used to the y equals mx plus b model. But anytime you have a linear equation with two variables like this, where your x term and your y term are on the same side and your constant is on the right side or vice versa, the easiest way, the quickest way to find 2 points, and it's so simple, is to use each of your intercepts. So you say, okay, I'm going to let x equal 0, and when x equals 0, 2y equals 2, y's got to be 1. Boom, 0, 1, you plot it. Then the other case is let y equal 0, cover up 2y, x is 2, 2, 0 is your x-intercept. You've got 2 points, draw a straight line. Some people usually like to find a third point just in case they made a mistake, but most of the time finding the intercepts is a pretty straightforward equation to solve. Again, the second equation, when you let x equal 0, negative 2y equals 6, so y is -3, so you have the point 0, -3 to plot. And then let y equal 0, so this is a big 0, x is 6. Boom, 2 points just like that. You draw your 2 lines, and there's your intersection. Okay. So do we have any questions at all on finding a common solution for a system of linear equations graphically? Let me show you what this would have looked like if you had a graphing calculator and you were just looking at the table, for example. So let me get out the graphing calculator. Here we go. And let's put in those 2 equations. We'll put one into y1 and one into y2. So one of them was, so here you have to solve for x. So I took the first equation and I solved it for y. So we're going to call this y1 and this y2. So I'm going to put y1 in, which is -0.5, -1/2 x plus 1. That's what I get when I solve that for y. And now I'm going to put y2 in and I get 0.5x minus 3. So if I graph this, I will see exactly the same thing you see. But let's look at the table to see what the table would look like in helping me identify. So when x is 0, y1 is 1, and y2 is -3. y1 does not equal y2 there. When it's 1, it's 1/2 and -2.5. Doesn't equal there. But if you notice, if you go up to this x equal 4, you see y1 and y2 have exactly the same value. So when x is 4, both in the first equation and in the second equation, you get exactly the same answer. So that's what we would do if we were using a table and trying to find the common solution. So this is the type of question you might see like on MyMathLab homework. They'll give you a table like this and they'll say, what's the common solution to the system? Any questions on that? I'll take a picture of that and put it in your notes. All right, so let me get that up and we'll take a little picture. So you could see, have that for your notes. All right. I didn't ask it to go to a new page. Oh, I forgot to change it. Okay, so I'll just cut it and put it on the first page for you. Okay, there we go. So I'll put that down here. Okay, and we'll highlight where the common solution is here. So right here, when x is 4, both y's are the same. So there's the common solution as well. All right. So today we're going to focus on a system of linear equations in 2 variables. You could have 3 variables like x, y, and z, but in order to solve for the common solution for x, y, and z, how many equations? What's the minimum number of equations you would need? 3. So the minimum number of equations has to match however many variables you have. Okay. So let's take a look at this first example, where we're now going to be looking at two equations simultaneously. In fact, when I was growing up, they were called simultaneous equations when I was in school. So now they're just called a system of linear equations. So this picture tells you everything you need to know. You have, if you look at the axes, you can see that along your horizontal axis, it's the number of years after 1970. So we're right about here right now at 2016. We're right about there. And along your y-axis is the percentage of American adults. And one of these equations, this very first one, models, note it models the percentage of married and never married US adults. So looking at this rather quickly, what kind of things does this picture tell you? What sort of observations do you make from this graph? Ian?
Never married are going
Are increasing, yeah.
And the married is decreasing.
So the percentage of never married are increasing, and the percentage of married adults are decreasing. Okay, good. Anything else you could tell me about this picture? Anything else? It doesn't add up to 100%. Never married and married. And what might be the other category? Yeah, divorced. And you're right, it doesn't add up to 100%. So they may have divorced in there or married multiple times. So maybe it's married once. That's an interesting observation. I hadn't actually thought about that. Okay, so let's see. What else can you tell me? All right, so eventually, that's a good thing, eventually. So eventually means we're beyond our data set, aren't we? Right now, if we drew a vertical line like you did with GeoGebra straight down through 2016, anything that you talk about after that time is an estimate or a prediction. So if this trend held, if these equations were true beyond 2016, that's the eventually, we predict that the percentage of each, right, of each of these population, of each population will be equal. And in fact, we may want to go beyond that and say at some point, it tells you that the percentage of never married is going to exceed the percentage of married. But we really don't know if this trend is going to continue. In my mind, when I look at this, I know that for most of my life, all marketing was geared towards the baby booming generation because we were the largest percentage of, we were the largest percentage in the population. But now we're starting to die off, people on the other end of the baby boom generation. And now probably marketing and looking at things in terms of a focus will be on the next largest population for us. I don't actually know what that is, if it's millennials or X generation, I don't know. The ones with the money, right? So anyway, these are the kinds of things you can look at when you look at models like this in terms of the graph. So let's estimate, because that's all we can do now. Let's estimate the common solution, which is this intersection point for this system of linear equations. Someone want to give me, other than Ian, an estimate for the number of years after 1970, which is our first coordinate, and the percentage, which is our second coordinate? There's no right or wrong answer here. We're just trying to estimate that point right there. Cornelia? 68 and 37 looks good to me. Okay. So this intersection point tells us what Danielle mentioned, that eventually we predict that the percentage of each population will be equal. So using now the numbers, we could say this. We want to talk about both variables with the appropriate numbers and the units. So notice you had to do a question like this 4 times for your project. So let's see how we would state this. And there's lots of different ways of stating this. So 68 years after 1970, well, 60 years is 2030. So the model predicts that in 2038, that's this number, the unit being the year, the percent of,
Between 2037, that's 37.
no, 68. Okay, so let me just finish this. If I make a mistake, could you just remind me when I'm done with the sentence, and then I'll be glad to edit it? Okay, so let me see, I'll go back to my thought here. The model predicts that in 2038, 37% of the population, no, that doesn't work. I want to say it in the best way possible. The model predicts that in 2038, the percent of never married and married U.S. adults will be 37%, something like that. If you go back to my first class, the sentence was different because everybody says it a different way. Okay, so what's the problem with this? There's no problem with finding the solution this way if we're just trying to estimate. And often a graph you can't get. In fact, I was working with a student in the studio who was trying to look at a graph with temperatures of 2 different cities, and she was trying to estimate this point. And it's hard when you're trying to estimate. I mean, if it falls directly where a vertical and horizontal line intersect both scales, it's easy. But in this case, you're estimating, and it's not the exact answer. If you want the exact common solution, you have to use algebra. And there's 2 different algebraic methods to solving this equation algebraically. One is called substitution, which many of us were doing on Friday when we were given a total and we were getting one of the amounts of money we were looking at in terms of the other. We were saying things like x plus y equals 3,000, and then we said y equals 3,000 minus x. We were actually we're going to use this substitution method for that. But anyway, some of you may be familiar with this second term as elimination. I'm not quite sure what most schools are teaching this day. Our book calls the second method elimination. Excuse me, addition. I grew up calling it elimination. Can you tell me which of these, how many people grew up or studied this with addition as the name of the process? 2 on this table, a couple on this table. Elimination? Both? Okay. All right. So part of what it's kind of nice to have both of these in mind, because addition sort of gives you a sense of what the mathematics is behind the process, and elimination kind of tells you what's actually happened once you apply this concept. So it's kind of nice to have both of them in mind. So when we see a system like this, if I had this system, I would probably use elimination or addition, but substitution is perfectly fine too. So one of the students in my first class said, is it all right if I just use the one I like to use? Absolutely. Some people just use substitution no matter what the system looks like. Some people use addition or elimination no matter what the system looks like. And some people are comfortable going back and forth. It's absolutely fine with me. However you do it is fine with me. Okay? So when I look at this system, let's talk about the substitution method. The substitution method is very handy when you have one of your variables with a coefficient of 1. So for example, in this first equation here, I see the coefficient of x is 1, which means I can solve this equation for x, and this is how we say it, for x in terms of y. So I make an equivalent equation where I just have x on my left side, and I subtract 2y from both sides, so I get 142 minus 2y, or minus 2y equal plus 142. Either way is fine. Okay? However you want to write it. Then the idea is, because I now have x written, expressed in terms of y, I can take that expression, this expression, or this expression, and put it into my second equation wherever I see y. So I'm just going to throw that into my second equation. So I'm going to substitute. Oh, thank you. So I'm going to take that expression and substitute it wherever I see x in my second equation. So I substitute, and that's the name of the process, substitute for x in terms of y. And what that gives you is one equation with one unknown, which we know how to solve, no problem. So now it looks like this, -3, and instead of writing an x, I'm going to write -2y plus 142, or 142 minus 2y, whichever you prefer, plus 10y equals 160. So now I'm all set. It's one equation, one unknown. I've known how to solve these types of things for a really long time. So I get 6y plus, check my mathematics here. That's minus 462. So I have to distribute the negative. Plus 10y equals 160. 426. Thank you. See, I told you to check me out. 426. Thank you. You have your calculators, I can see. 426. So 16y equals, check me on this one too, 586. Is that correct?
Correct.
Woohoo! Now divide both sides by 16 and I get 36.625, or as a fraction, 36 5/8. So roughly a little bit more than a half year beyond 2036, we're saying that that's when the never married population, the percentage of never married will equal the percentage of married. However, have I found the common solution? No, because I've only found the value for the y variable. I haven't found the value for the x variable. Okay, so to do that, and this is important, you always go back, always go back to an original equation. Because if along the way when you were, changing this equation and making it in terms of y, and you made a mistake and then you put it into your second equation, if you don't go back to the original equation, you'll never find out that you made the mistake. So always go back to an original equation. Now you want to substitute y equals 36.625, and now you'll solve for x. So I'm going to go back to my first equation, which is much simpler to solve for x. So it's x plus 2 times y is 36.625 equals 142. So now I multiply 36 times 36.625 by 2. 36.625 times 2, and I get 73.25 equals 142. And now I do 142 take away 73.25, and I get x equals 68.75. So they're saying in the year, a little bit more than halfway through the year 2000, 36 years added to 1970. Something's wrong. Oh, what? Oh, this is the, see what I did? I'm so used to solving for X first. I totally reversed it. So I knew something was wrong because we had already looked at the graph, right? This is the percentage and this is the year. Phew, okay. So the common solution here is 68.75, and that represents the number of years after 1970. Now that makes a lot of sense. So a little bit more than halfway through 2038, and the percentage is 36.625. So that's the percentage of US adults. All right, so notice what I've done here. And this is a little handy dandy strategy for the interpretation of these. Once I found my solution underneath, because I often don't have enough room right beside it. So underneath, I actually write the units for that particular number, since our interpretation has to include both of the numbers and the unit. So underneath, I said 68.75 represents the number of years after 1970, and 36.625 represents the percentage of US adults. So now when I go to write my interpretation, I have all the information that I need. Okay. Any questions on that with substitution? Okay, let's take a look at the addition method. And I'm just going to go on to the next page. So let me get a little copy here of this system, so I don't forget what it is. All right, so there we go. So now the addition method is a little different idea. And I'm going to give you two trivial equations, 3 equals 3 and 5 equals 5. And the addition method says that if I add both sides, I still have an equality. So that's the idea behind using the addition method. So right now, if I were to add the left side and the right side together, I would get negative 2x plus 12y equals 302. So that's still a true statement, especially if I knew what x and y was. It would be a solution to all three of them. However, this still doesn't help me to add the left side and the right side, because I still have one equation with two variables. So now the goal is the second part of that name, elimination. Can I add these two sides together in such a way that I eliminate one of the variables? So to eliminate one of the variables, the coefficients in front of each of these, or one of these, must be opposite. So I use the powerful tool available to me for equations, which means I can multiply or divide both sides of any of these equations here by a non-zero quantity or number. So since x already has a coefficient of 1 and a coefficient of -3, and they're already opposite in sign, I'm just going to do a little plastic surgery on my top equation here and create a -3 in front of it. So I'm going to write an equivalent equation by multiplying both sides of this equation by 3. And I get 3x plus 6y equals 624. 426. Okay. Now, I don't write it on top of that because it can get all confusing. So take what is it? 10 seconds to rewrite your second equation like that. And now when you add both sides, this goes to 0. So you've eliminated the x variable. Okay. And you get 12y equals 586. 16y equals 586. Boy, my adding and division is a little off today. Yeah, well, This is what happens when you have those Patriots and Red Sox games all in one day, you know? Yeah, so y equals, we actually know the answer to this because we've done it before. Y equals what? 68, no, 36.625. And when we substitute back in, we get 68.75. Is that correct? Okay. So you pick what works. Sometimes one method is a little easier than another. For example, if all the x's and y's had coefficients and they were all different than 1, and they were kind of high numbers or numbers a little bit bigger than like 2 and 3 or 10 here, it might make sense to use addition or elimination. Sometimes you have to multiply both equations. For example, if this second equation here didn't say -3, then I may multiply the top by 3 and the bottom by -1 just to create the opposites. See, sometimes you just have to like look at what's given to you and then make a decision. And that just comes with a little bit of practice. Right? So let's take a look at a similar problem to what we looked at Friday. Okay, but now we get to use 2 variables instead of 1. These, I think on Friday, I don't know what the story was. I think it was a scholarship story instead of an investment. Like I said, the process for solving these often is exactly the same. It's just the story that changes. So how you define your variables, what changes. Some of you may be familiar with this sort of table idea that we use in Math 096 to do these types of problems. This is exactly like what you would have seen in 096. It should be nothing new if you've had intermediate algebra with us. So what's going on here? We're investing a pot of money, $10,000. We're going to put some of it in a low risk fund and some of it in a high risk fund. There's your 2 different amounts. One's going to be a little bit bigger than the other because we want to invest a little bit more into the low risk fund than the high risk. So if you have a table like this, notice your column heading defines each of your variables. It's the amount invested in dollars. It tells you the definition in terms of a quantitative description, and it has your units. Then on your in your first column, it tells you what you're looking at. You're looking at a lower rate fund and a higher rate fund. So if I do this right now, I have totally defined my first variable. So some students like doing this because they don't like doing this. X is the amount, I don't know why, of money in dollars invested in the low risk. Maybe you just don't like writing, I don't know, the low risk fund. So do you see that this description of X and putting X in this cell all says the same thing? What's critical is you know what each of the variable expressions, and you've got 4 of them in this case. You have 2 descriptions of the amount of money you're investing and 2 descriptions of the amount of interest you're investing or earning. So first I say I'm going to put X into the low risk fund, and instead of now writing 10,000 minus X, which we had to do on Friday, I'm just going to say Y. It's kind of like, feels like a little bit like a cop-out, but it works. And now once you write one sentence, you can use ditto, 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 high risk fund, okay? All right. So I mentioned you have 4 different algebraic expressions to define. Here's the first 2. Your next 2 has to do with the amount of interest. See, first you have the amount of money invested and then the amount of interest earned. So the amount of money invested and the amount of interest earned after 1 year. Well, to find the amount of interest, you have to know your percent rate for each one. So 4% and 8%. And again, the only mistake I tend to see here is students sometimes might call this 0.4 and 0.8. They just convert their percentage to a decimal incorrectly. So be careful with that. Now, the amount of interest earned on X dollars, the amount of interest earned on X dollars is this expression, 0.04 times x. So up here, if I'm writing this out, if I don't have a table and the teacher says to get full credit, define all variable expressions, I would put 0.04x represents the amount of interest in dollars earned on X dollars. And you could say invested in the low risk fund. If you want, it's not necessarily because you've already defined what X is. What would be the amount of interest earned on the high risk fund? 0.08, what? Y, because Y is what I've invested in the high risk. And again, notice if you just multiply straight across the row, 0.08Y equals the amount of interest earned in dollars on Y dollars. However much I put in, I take 8% of it. Now, what's critical, folks, is you would never just see over here 0.04 and 0.08. They have no units on them. They're unitless. This column has to represent dollars. So the only way you're going to get dollars here is to take a piece of some amount of dollars, some fraction of it or some percentage of it. So it's really critical that you never see an equation with just 0.04 or 0.08 because you're adding like things. So now to come up with your system, once you've created your four expressions, you say, what equals what? Well, my first what equals what comes in the first column. When I add the amount of money I invested in each fund, I have a total of $10,000. So voila, my first column gives me my very first equation. So my first what equal what deals with the total amount of money invested, total money invested. The second idea that I have in my equation is the total amount of interest that I earn, which is my last column here. So my what equal what here has to do with the total interest earned in 1 year. So if I take the amount of interest that's earned in the low risk fund and I add that together with the total amount of interest in the high risk fund, what total do I get? 550. So that's my second equation. So voila, I have my two equations with two unknowns. So I now have to solve that system. So again, how you solve this is totally up to you. I'll get you going, and then I'll put the answer up later while you're working on your class activities. What did you do Friday? You actually did this on Friday. You solved this equation for Y. You used substitution, because on Friday you said Y was the total, take away the amount of money invested in the low risk fund. So you take that first equation, you can solve it for either X or Y. Notice earlier we solved it for X, now we're solving it for Y. And now you take that value for Y and you substitute it into the second equation. So now it looks like this, 0.04X plus 0.08. Now instead of Y, you put 10,000 minus X equals 550. So you get 0.04X plus 800 minus 0.08x equals 550. Negative 0.04x equals negative 250. And x equals 6,250. So I found x. I go back to one of my original equations right here, 6250 plus y equals 10,000. So y equals 3,250. So my common solution is this ordered pair, 6250 and 3250. So I'll always ask you to answer any of these problems with a sentence. So you would say, I invested $6,250 in my low risk fund and $3,250 in my high risk fund, period. So you have 5 problems and you have 23 minutes to work on them. I would suggest try one of the break-even problems. Once you get one of them done, leave the other one and move ahead so that if you have any questions on the problems, you can get them answered while you're in class, okay? Any requests for music?